In this tutorial, we're going to take a look at some algebraic properties, and then we're also going to use those algebraic properties, or some of the algebraic properties, to help us justify the steps that we take when solving an equation. So here on this first screen, it says, name the property demonstrated by each statement. Now, these examples and the properties that we're going to go through are not all of the number properties or the algebraic properties, but they just kind of represent a sample of some of the properties that we would see, and so I thought we could go through those. The first example we have here is 3 added to 7 is equal to 7 add 3. And notice the order has changed in those two examples, or the two sides. The order is reversed, but we still end up with two sides that are equal. That's an example of the commutative property of addition. The next equation we have is 5 added to the group 3 plus b, and that is equal to the group 5 added to 3 plus b. And you'll notice the grouping has changed, but the two sides are still equal to each other. That's an example of the associative property of addition. The next example, we have 27 multiplied by 0 is equal to 0. And if you remember, no matter what number we multiply by 0, the product is always 0. That's an example of the multiplicative property of 0. In the next example, it says, if 4 to the x is equal to 4 to the 7th power, then x is equal to 7. Notice the bases are the same, and if so, then we can use the exponential property of equality to state that x is equal to 7. The next example says if 6x is equal to 36, then 6x divided by 6 is equal to 36 divided by 6. Notice we're dividing both sides of the equation by the same value. That's an example of the division property of equality. Next, we have 32 added to a negative 32 is equal to 0. 32 and negative 32 are opposites of one another, and we call those opposites additive inverses. The sum of a pair of additive inverses is always 0 because the two numbers are opposites of one another. And the next one, we have 3/7 multiplied by 7/3 is equal to 1. So notice we're taking two fractions and multiplying them together, and the product is 1. Whenever you have a product of 1 like that with fractions, then we can say that the two fractions are multiplicative inverses of one another. The product of two multiplicative inverses is always 1. And then last one here we have, if m is equal to 8, then 8 is equal to m. Basically, we're saying the same thing, just one equation has m in front, the other equation has 8 in front. That's just an example of the symmetric property, equivalent statements. Okay, now in this next part here, we're going to justify each step of the following solution of an equation. So all the steps are given. We have our original equation all the way down to the solution. And one thing I wanted to point out here is right here is the original equation that we're going to be working with. And right down here at the very bottom, well, you'll see it here in a second, is the final step, or the final result as far as our equation. But all the way along, we have these simplified equivalent equations as we work our way to the final solution. So that's basically all we're doing, is using these steps to simplify the equations till we get down to the solution. Okay, so we start with the equation x added to 16 is equal to two groups of x add 5 plus 2x. So if you look under the steps column, the equation is now x add 16 is equal to 2x add 10 add 2x. Notice the parentheses are no longer there, because what we did was we said two groups of x plus 5 is the same thing as taking the 2 and multiplying it by x to get 2x, and the 2 added to multiplied by 5 to make 10. So multiplying the 2 through the parentheses is the distributive property, so we use the distributive property to get to that step. If you look carefully in the next step, we're subtracting x from both sides. We want to, we can do that because we have x's on both sides, but we only have one x on the left side of the equation, so 1x is the maximum number of x's we can take away. But since we're taking away the same number of x's, that's an example of the subtract property of equality. Right here we have x, and we're taking away x. X and negative x, you could look at it that way. They make 0. And so here in the equation we have a 0 because x and negative x are additive inverses. Notice that in the next step 0 is gone because 0 added to 16 is just 16. That's because the additive identity tells us that no matter what number you have, if you add 0 to it, its value doesn't change. Now we're beginning the process of isolating the variable. So to make the positive 10 go away, or to eliminate, we can just subtract 10. Notice we're subtracting 10 from both sides to maintain balance. That again is an example of the subtract property of equality. A positive 10 and a negative 10 make 0. They're additive inverses of one another. 3x added to 0 is 3x, because no matter what the number is, if you add 0, the number doesn't change. That's the additive identity. Now, we know that 6x's are equal to 6 is equal to 3x. To find the value of a single x, we just divide both sides into 3 groups. Dividing by 3 on both sides is an example of the division property of equality. 3 divided by 3 is 1. So dividing by 3 is the same thing as multiplying by a third. 3 and 1/3 are multiplicative inverses of one another. Their product is 1. That's where the 1 comes from. Now 1 multiplied by x makes x. So no matter what number you have, if you multiply it by 1, the number doesn't change its identity, its value. That's an example of the multiplicative identity. So the equation 2 equals x has been replaced with the equation x equals 2. Those are equivalent statements. That's simply using the symmetric property. And so that we're just going through that. It kind of helps us practice justifying our steps using the different algebraic properties.